In this video, I'm going to talk about calculating energy in simple harmonic motion. Take a moment to read the success criteria I plan to cover in this video. So let's just remind ourselves of the conditions needed for simple harmonic motion. The first one is that the acceleration or force is always towards the center. So if I'm over here at A, that means my restoring force is going to be trying to bring it back to the equilibrium line. The force will be to the left, but my displacement is over here on the right. Likewise, if I'm speeding up in this direction, my acceleration will be negative. Speeding up in a negative direction, it would also be towards the left. The other part is that the acceleration of the force is proportional to the displacement. In other words, the farther I move away from the equilibrium, the larger the force will be, or the larger the acceleration will be. So here's our pendulum, our example of simple harmonic motion, and it's going to go from A to C to E. In this case, we have two different types of energy as it moves through one oscillation. When it starts up here, it has no movement, but it does have gravitational potential energy. As it swings down, once we get to C, it doesn't get any lower. So at this point, we're going to say there's zero gravitational potential energy, and then as it moves through, it will go up to its maximum again at E. We're going to assume there's no friction, there's no reason for energy loss. So A, gravitational potential energy, I'm just going to write maximum here. And C, there was zero. E, maximum. C back to zero, and then back to another maximum at A. Remember that energy is a scalar, so it doesn't have a direction like force and acceleration. So a maximum just means a maximum magnitude. There's neither positive nor negative. Well, we also were talking about it moving, so there must be kinetic energy somewhere in the cycle. At A, we have zero kinetic energy because it stopped. At the bottom, this is where our kinetic energy is max, and I'll fill the rest in. Right now we're just talking about this qualitatively, but later we'll do the equations so that we can do it quantitatively as well. So what if I have a different simple harmonic system? Well, now we've got our spring and mass. And again, I'm going to have kinetic energy because it will be moving. But now instead of gravitational potential energy, I will have elastic potential energy. So let's think about taking this mass and moving it over to A and starting from here. Now I've compressed my spring. That means my potential energy will be a maximum, but it's not moving, so I have zero kinetic energy. Once I let it go and it goes towards the equilibrium, at C, the original length of my spring, there is no potential energy, but I have a maximum kinetic. When I move all the way to E, now it's at its maximum extension, and I'll have a maximum potential energy again. It stopped, no kinetic, so let me fill in the rest of these. Now you might not have realized, but this is the exact same table we had in the previous slide. It doesn't matter which simple harmonic oscillator I have. I'm going to have energy being changed between kinetic energy and a potential energy. The only thing that changes is the kind of potential energy I have. Well, that was fine for qualitatively, but we're going to have to calculate this as well. Let me just remind you, in a previous video, I went through for a pendulum to calculate the period, and for a mass spring system, we had a different equation that we could also use to calculate the period. Why is that important? Well, omega is 2 pi over t. So in our equations here, this would be total energy. I have 1/2 the mass times omega squared for pi squared over t squared. And x naught, don't forget, that is the maximum displacement possible. And down here, I have the potential energy. Again, depending on whether I have a mass spring system or pendulum will change how I calculate the period, and that's how I'll get omega. So this equation still remains the same no matter which simple harmonic motion I have. One difference I want to point out is for the total energy. Notice these are all constants: the mass, the angular frequency, and the amplitude. So during our simple harmonic motion, the total energy is constant. But the potential energy will change, because this is no longer x naught. This is the displacement at where I want to get my value. So for example, it could be A, B, C, D, or E. It could be anywhere. At C, x equals 0. At A and E, x will equal the maximum x naught, and so B and D are somewhere in between. So let's do some examples. I've got a pendulum of mass 100 grams. Now, let me point out that we need to put that into kilograms. Why? Because I want my answer to be in joules. And joules has hidden inside kilograms, meters, and seconds. It has a period, that's capital T, of 0.5. And the amplitude, x naught, is going to be 0.1. So, part A, calculate the angular frequency of the pendulum. Omega is what we're looking for, 2 pi over the period. That's going to be 2 pi over 0.5. And if I pick up my calculator, that gives me 12.6, and the units will be radians per second. Remember, that's the difference between angular frequency and frequency. Angular frequency is the number of radians per second. For part B, the total energy, so now let's write the equation we just have. It's found in our data booklet. I'll substitute in my numbers. And again, if I pick up my calculator, I'm going to get 0.079 joules. And finally, it asks me for the kinetic energy. I need some more space here. Now, the equations I gave you were total energy and potential energy, and there wasn't one for kinetic energy. Let me point out, we only ever had kinetic energy or potential energy. So I want to calculate the kinetic energy. I'm just going to take the total amount, subtract off the potential. I have these two equations, and then what must be remaining is our kinetic energy. So 1/2 m omega squared x naught squared minus 1/2 m omega squared x squared. Now let me just collect some like terms so I don't have to do as much substitution. We have 1/2 m omega squared is common both, and then I just have x naught squared minus x. And if I substitute in my values, picking up my handy-dandy calculator, I get 0.060 joules. Notice I want to point out that the displacement is at only half the distance to our maximum, but notice that the energy is not necessarily half of the total. And that's because our force is not a constant force. And moving the last 0.05 meters is not the same as moving the final 0.05 meters, 0.5 meters. Okay, one more example, and now with a mass spring system. We have this mass spring system with a period of 1.2. It's extended 0.05. So in this case, that will be my maximum amount. And the mass is 250 grams. Remember, we need to put that into kilograms, so our energy will be in joules. The first part says, calculate the potential energy stored in the spring. So using my potential energy equation, and I'm going to substitute in my values. Picking up my handy-dandy calculator, I'm going to write extra significant figures for now. 8.57 times 10 to the minus 3 joules. If you look I have only one significant figure here, 2, maybe 3, it's ambiguous, 2 here. Our answer here really should have 2 significant figures. Don't go less than that, because we want to match our data. The only thing that should have only 1 significant figure would be an uncertainty. So this on a real exam would probably be written as 0.50 to show you that there was 2 significant figures. Now it says the spring is extended another 0.5 meters. Calculate the new total energy. Remember, in this case, my potential energy was the total energy because I extended it and I hadn't let go of it. I'll substitute in my answers. So remember, here we doubled the extension, and I have not just doubled the amount of energy. In fact, it's a lot more than that. Remember, compressing the first 0.05 is not the same as compressing the next 0.05. It takes a lot more effort to move the next bit. Let me put my answers up here so I can erase this and have a little bit more space. And finally, it says calculate the new maximum velocity of the mass. Now, I want to show you something else. Kinetic energy equals 1/2 mv squared. We know that our kinetic energy, if I'm at the maximum velocity, the total energy is going to be kinetic energy. So I can just use this exact same equation like I would normally do, even though we're in simple harmonic motion. That means V will equal 2 times the kinetic energy over the mass. I need to get the root sign in here. And I get a value of 0.52 meters per second. I want to point out one more thing. So yes, I can use this equation, kinetic energy is 1/2 mv squared, but remember we also have this. Kinetic energy is going to be 1/2 m, and I know how to calculate my speed depending on where I am. From our data booklet, we know that V equals plus or minus omega square root x naught squared minus x squared. So if this is V, there is V squared. If I expand this out, I have 1/2 m omega squared, and then I just have x naught squared minus x squared. And if you remember from example number 1, this is just total energy minus the potential energy. So it still all works out. Please read the success criteria one more time, and I hope that you can say yes to these bullet points.